Okay, let's try something else today, which I think is kind of cool. Let's look at this series right here. I warned you that this was coming, or maybe the better word is promised you that this was coming. So on. There it is. There's an infinite series, and we want to know whether when you add all those things up, whether it goes off to infinity, becomes arbitrarily large like the harmonic series did, right? If these were not squared, but just one, 1/2, 1/3, 1/4, then we know that those don't get small fast enough, and so the whole thing ended up going off to infinity, right? Remember that proof? You should know how to do that proof on your own. Okay? Go back and try to do it on your own. Remember, you want to pull things together, group things together which are together in a size greater than 1/2. You keep going like that, okay? Anyway, how about this one? Then we also had the geometric series. 1, 1/2, 1/4, 1/8, 1/16, and that one converged. This one's kind of in between, okay? These terms get, the denominators get big fast enough, kind of in between the other two, and so 1 over that gets small, kind of in between the other two. They get small faster than the harmonic, but they don't get small as fast as the geometric. So does that converge or not? Well, let me show you something kind of cool. Here's the graph of 1 over x squared right there. You know that it looks something like that. And so if I just mark off 1, 2, 3, 4, 5, 6, and so on, and then I look at what happens when I form these rectangles right here. What are the areas of those rectangles going to be? Let's figure them out. This rectangle happens at 2, so the height of it is 1/4, and the base is 1, so the area of that is going to be 1/4. Here it's 3, so it's 1/9 times 1 is 1/9. It's going to be 1/16, 1/25, 1/36, and so on. See that? So these things right here, all the terms of this sequence, except for the 1, lie underneath this function. Okay? Well, how is that helpful? Well, remember that a couple sections ago, we proved that the area underneath 1 over x squared from 1 to infinity was equal to what? Going from 1 to infinity, the antiderivative was 1 over x, and we go from 1 to infinity. As x goes to infinity, it's going to be 0. Subtract 1 over 1, and you're going to subtract that, and it's going to be 1. So the total area underneath this graph from 1 to infinity is equal to 1. So the total area underneath that whole thing going all the way out is 1. And so I know then, just by comparison, that if I add these numbers up, 1/4 plus 1/9 plus 1/16, going all the way out forever, that's going to be, this thing here is going to be less than or equal to, well, let me say it one more time. All this going all the way out is less than or equal to 1. If I add 1 to it, it's going to be less than or equal to 2. See that? Is that clear? So 1/4, 1/9, 1/16, 1/25, all of these things going all the way out, that had to be less than the area underneath this function right here. Look at the rectangles, And so all these things are less than 1. Let me just write 1 plus 1 just to kind of make it clear. So here's the 1 from here. That's less than or equal to 1. And so the point is, we know 2 things. We know the value of this integral is less than or equal to 1, and we also know, we know that it converges. That's maybe the most important thing. We know it converges, and then we know what it converges. Well, we don't know what it converges to. We don't know what it converges to, but we do know it converges to something less than 2. Okay, that's often important. If you know that gets you a long ways quite often. If you can make a bound for it and say, not only do we know it converges, but we know it converges to something smaller than, in this case, 2. Okay, so there you go. By the way, it's known through other methods, which are kind of clever, that this thing actually converges to pi squared over 6. Okay, you'd never guess that. But go ahead and add these things up as far out as you want and see once how close you get to pi squared over 6. That's what it actually converges to. In fact, I'll tell you, well, I'll get to that. Well, okay, that's good. 1 over n cubed, what can we say about that? Well, each one of these values is 1 over n cubed. Each one of these is less than or equal to 1 over n squared. And so when you add up all these things, if this converges to something less than 2, then it's got to be the case that if I were to take these right here, which are going to be 1 plus what? 1/8 plus 1/27, and so on. Those are going to have to add up to something yet less than this one. Okay? And what's kind of interesting is, for even powers here, as far as I know, we can kind of figure out what they converge to. At least n squared we can, and I think I remember reading that you can for all even powers. I haven't done it myself. But I also know that for odd powers, even though we know this converges, we have no idea what it actually converges to. We can get something close, but we don't have the actual value that it converges to, which is kind of interesting. Okay? So anyway, so there's that one. Okay, so that converges. Now, what about in contrast, this one right here? So that's going to be 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over the square root of 4. I guess the square root of 4 is 2, so I can actually put that down. 1 over the square root of 5, and so on. Okay? Does that converge or not? Well, let's try something similar to what we did before. Okay? If I look at this function right here, which I attempted to draw, f of x is equal to 1 over the square root of x, has the same shape as 1 over x squared, then let's do the same thing as before. Here's 1, here's 2, here's 3, 4, 5, 6, and so on. Okay? So what if I try to do the same thing as before? What if I say, okay, this thing right here is going to have area 1 over square root of 2. This is going to have area 1 over the square root of 3, 1 over 2, 1 over the square root of 5, and so on. Is that going to be able to get me a conclusion the way I had before? Well, let's think about it. What do we know about this function? Do you remember? This was the p-test. This is 1 over x to the 1/2 power dx from 1 to infinity, which is x to the minus 1/2 dx from 1 to infinity. How do you find the antiderivative of that? As always, you add 1. If you add 1, you're going to get x to the 1/2 divided by 1/2 is times 2 from 1 to infinity, which is 2 times the square root of x from 1 to infinity, which, as x goes to infinity, that goes off to infinity. So what do I know? I know the area underneath this graph is infinite. Okay? Are you with me? The area underneath that graph is infinite. If the area underneath this graph from 1 to infinity is infinite, what do I know about the area underneath these rectangles? There are some very important times in mathematics where the right answer is we don't know. And that's what you should have answered. Should have answered the area underneath this thing is infinite. The area underneath these rectangles, it's less than that. Well, heck, if it's less than that, you've got all the possibilities in the world. It could be it could be infinite, which is another, it still could be infinite, or it could be a finite number. It could be anything. If you ask what's less than infinity, well, or less than or equal, I mean basically, if you have, you can either have infinity is less than, shoot, I'm getting, if this thing has an infinite area, this could also have an infinite area. That's certainly a possibility, but it also could be a finite. It could also be a finite area, okay? So drawing these rectangles in this case doesn't do us any good, okay? But, wait a second. All hope is not lost. Look, instead of drawing them that way, all you have to do instead is draw the rectangles this way. Use the left-hand sum here. Okay? Now if we use the left-hand sum, notice that this is 1 by 1, so the area underneath this rectangle is 1. The area underneath this is 1 over the square root of 2, 1 over square root of 3. That's going to be 1/2. And so on. That's a perfectly good picture. That picture does me a whole lot of good. Because look, I still know that the area underneath this curved graph is infinite. And now I've got these numbers right here, which correspond exactly to these. See that? They correspond exactly to those. And so this contains the infinite area. Here you have an infinite area right underneath that graph, so obviously the area underneath those rectangles has to be infinite. So from this we can say, this thing right here has got to be greater than or equal to this integral. And that thing went off to infinity. See that? So you can get a result either way. The way you get the result is just being judicious by the choice of whether you want the graph to go above or below. And one way or the other, you can get the result you're after, okay? And the real key to this, is just understanding these pictures, okay? Understanding these pictures. So let's do let's give a more general result now. By the way, I know what I was going to say. By the way, we could have gotten the fact, if look at this. Let me just state this. The square root of n is less than n. Agreed? Less than or equal to n. When you take the square root, it's going to be less than or equal. So 1 over the square root of n is going to be greater than or equal to 1 over n. These are bigger than these. And so since these are bigger than these, I know that if I add up all these things, that goes off to infinity. So here's what I can say. I can say that this sum right here, going from 1 to infinity, when you add all those up, that's got to be greater than or equal to what happens when you add up all these things. And what happens when we add up all those? Hopefully you remember, that's our harmonic series. That's the harmonic series. That's the one that goes off to infinity. So just by comparing it to another one, we were able to get the same result. Okay? So this whole lesson is basically just looking at lots of comparisons, just comparing it to integrals or comparing things to other series. So here's the theorem I want to write down. Okay. What kind of functions will this work for? What if I have a function that isn't quite so nice and smooth, but it still looks like this? Will I still be able to make comparisons? Yeah, if I take the left or the right sums, let me do both of them. I should have a different color here, but I guess it doesn't really matter. See that? The left-hand endpoints contain the area underneath the graph, and the graph contains the area underneath the right-hand endpoints. See that? So that's exactly what we had working for us in the last two problems. As long as you keep that same pattern all the way, you're good. On the other hand, what if you had a function like this? Now, if you take the left-hand endpoint, notice that some of them are too small, don't contain the function, and some of them are too big. So you can't make any nice, easy comparison about the area underneath the curved graph versus the area underneath the rectangles. So you can't make a nice comparison. Similarly, if I were to go the other way, let me do it again. And if I were to take them going this way, see that? Some of them lie below, some of them lie above. Okay, I guess most of those, well, some of them lie each way. So again, then you can't make any nice comparison the way we did before. So we need a function which is going to be decreasing, always decreasing, never bouncing back up and down again. And might as well make it continuous just to make it easy to work with as well. And so here's what we want to say, something like this. Suppose a sub n is equal to f of n, where f of x on the interval, let's just say from 1 to infinity, is a decreasing, which means it doesn't have to be strictly decreasing, but decreasing continuous function. Okay? So then, this series converges if and only if this integral converges. In other words, if this thing converges, then this converges. If this thing diverges, then this thing diverges. One happens if and only if the other one happens. So they do things together. So all you have to do is check to see what this one does, and this is going to do exactly the same thing. Okay? So I'm not going to prove that, because the proof of it is just exactly what we did in the previous two problems. You either draw the rectangles up on top of the function, or you draw them on below the graph of the function, and you can get the result either way. Okay? So one quick corollary of that, I haven't used that I don't think in any of my calc videos yet. Corollary is a quick result from a theorem, okay? And so here's a quick result from a theorem. We have this. 1 over n to the p converges if P is greater than 1 and diverges if P is less than or equal to 1. Okay, remember the P test that we proved for, make sure that we're working here yet. Yep, very good. Remember the P test we had for integrals? That same thing now, because of this theorem, is going to apply here. So if you have any power of P greater than 1, then don't just remember the result. Realize why the result is there. Then these things are getting small fast enough that this thing converges. On the other hand, if P is equal to 1, you have the harmonic series. Or if P is less than 1, then these aren't going to go to 0 fast enough. And so this thing is going to diverge. And so we have that result. This is called the P test. Okay, called the P test. Okay. One of those things that you have trouble talking about the P test if you're in a junior high class, but hopefully, hopefully by the time you get to Calculus 2, you can talk about the P test without thinking junior high thoughts. Okay, very good. So there's that one. Let's do some other ones. Okay. So this is the theorem. I'm going to have to erase it just for the sake of board space here. Okay. How about that series right there? Well, you've got several options. One option is this thing. If you look at the graph of f of x is equal to 1 over x squared plus 1 on the interval from 0 to infinity, it looks like this. So it's continuous and it's decreasing. So all I need to do is to look at this right here. And I have to find the antiderivative. Do you remember the antiderivative? That is the arctangent. It's the arctangent of x from 0 to infinity. As x goes off to infinity, it's going to become the arctan of pi over 2. At 0, it's going to be 0. So the area underneath this thing is pi over 2. And so if you wanted to do I guess the most important thing is that since this thing converges, this is also going to converge. Okay, I'll just leave it at that. Okay, so it converges. Okay. Another way of seeing that it converges is by just noticing, oh, look at this. 1 over n squared plus 1 is always going to be less than or equal to 1 over n squared. Agreed? Because the bottom is bigger than this bottom. So this is going to be less than or equal to this. And so since this thing converges, this thing is going to converge. Okay? So because each one of these is smaller than these. And so since this adds up to a finite number, this is going to add up to a finite number smaller than or equal to that. Okay? So again, you make some comparisons. I've been using a theorem over and over again without explicitly stating it, but let's go ahead and explicitly state it. Theorem. Suppose we're talking about positive things here. So suppose you have these two series. One is made up of a sub n's and one is made up of b sub n's. And what's our result? If this thing diverges, then this thing's got to diverge. Right? Because each one of these is bigger than or equal to each one of these. So if when you add up these, it goes off to infinity. This has got to be the same. On the other hand, if when you add up these, if that thing converges, then since each of these is less than or equal to these, this has got to converge, right? I've already used that a couple times without just explicitly stating it. But there's another theorem which just gets in, it just shows the comparison of things. You just do comparisons. Okay? Let's try some more. I've got scores of these things. Some of my most interesting ones, and I just for sake of since I'm just teaching a class here rather than having you all in class and giving lectures, I won't go through all 60 or 80 problems, but there are a lot of good ones. I'll give you just a few of them. How about this one? Okay, you want to get, ideally, you want to get so that you can just look at it and say, oh, I know right away whether that thing converges or diverges. And the reason you know is because you have a repertoire of things you already know, and you can compare it to things you already know. That's the key. David Copperfield, the magician, once said, I saw him in a program, and he said, any 8-year-old could do my magic tricks with 20 years of experience, okay? And so similarly, I'd say once you have enough experience with these things, they're all easy. Any 8-year-old could do it with 30 or 40 years of experience, okay? So anyway, what did you see anything here? A couple things come to mind. One is, I think, oh, I'm kind of think I can see how you might evaluate that integral there. That looks kind of familiar. I can let u be equal to the ln of x, and so du is going to be 1 over x dx, and so this thing becomes u 1 over x dx becomes du. As x goes to infinity, the ln of x is going to go to infinity, and when x is equal to 1, the ln of 1 is equal to 0. So you just have that right there. And that one's a real easy one to integrate. That's going to be what? 1/2 u squared from 0 to infinity. As u goes to infinity, off she goes. Okay? So since this thing is infinite, you know that this thing is also going to diverge to infinity. Okay? Diverge to infinity. If you want to, you could write equals infinity there, which is saying, hey, it's just going off to infinity, becoming arbitrarily large. Okay? What's an easier way to have done it? Again, I've got a repertoire. Do you have that? You, I know because I've just been teaching you, have the same repertoire. So here's what I can say. I can say that ln of n is bigger than 1. At least it is once you pass e, I guess it is, right? And so the ln of n divided by n is going to be greater than, I'll say greater than or equal to here, greater than or equal to 1 over n. And now what do I know? I know that this thing here diverges, goes off to infinity, and these things here are bigger than or equal to those, and so these things here have to go off to infinity. See that? That's the idea. Now I said something really fast here. I said, oh, this is true not for all n, but for n greater than, I guess these are integers, so for n greater than or equal to 3. Right? Which is e is 2.7. So for n greater than or equal to 3, that's the case. So the fact that I had to start at 3, does that change anything? No, not at all. Whether a series converges or diverges doesn't depend on the first 5 terms or the first 50 terms or the first 500 million terms, right? Because the first 500 million terms, if you were to add them all up, that's going to be a finite number. So whether any series converges or diverges depends on, I call it the tail. It just depends on the tail. It depends on the stuff out there. So all these theorems that we have, so this is a good point. Suppose we want to compare an integral to a function that does this. Maybe it goes up and then it comes down like this. Well, can we not use the previous theorem because this is not decreasing? No, we can still use it because if this is 1 right here, 2 right here, 3 right there, 4 right there, 5 right there, 6 right there, and so on, then we see that from 3 on, this thing is decreasing. And so whatever that series is doing for those first few, it doesn't really matter. Again, what matters is from 3 on, if this is a finite number here, then the area underneath these rectangles is also going to be finite, and you're all set. Okay? Here's why Calc 2, this area really turns you into more mature mathematicians, because you have to understand the theorems. You can't just say, okay, here's exactly what it's saying, so as long as it applies to there, it's good. If it doesn't quite match it, then I can't use it, whatever. You might have to modify it and so on. You have to understand the principle of the theorem and use the principle involved. Being careful not to abuse it, you can't, but you have to understand it, okay? And so that's why this stuff is good. I love it because you have to know the answer before you begin. It's not like taking the derivative where you just do this mechanical thing and you say, okay, here's what I do. I take the derivative of the top times the bottom, da-da-da-da. No. When you see something like this, before you even begin the problem, you have to know what the answer is. I knew I knew that this would work to compare it to an integral. I also knew that it would work to compare it with 1 over n, but that's because I saw right off the bat that this thing was bigger than 1 over n. So I saw that right to begin with, and then the proof of it was just verifying what I could see in my mind. Okay, so we'll do a few more like this just to make the point. Okay, let's see, what are some other ones I have here? Here's one I've got. What about that one? Converge or diverge? Well, hopefully you're saying this thing here acts an awful lot like this. The 5 isn't going to make a whole lot of difference, and I know that this thing diverges. So my guess is this is also going to diverge. The problem is, if you try to find an integral like this to compare it to, I don't know of any. If there is one, it's kind of clever and whatever. So I should throw a dx on there. So that's not an especially useful thing to try. So that's not especially good. If we try to compare it, it would be nice to say that this thing right here is bigger than 1 over the square root of n, and then say, oh, I know that this thing here diverges. That would be great. Unfortunately, I can't say that this is bigger than this, right? This is smaller than this. So just because this thing diverges, when you add them all up, doesn't mean that those are going to diverge. These are smaller than these. Maybe these will converge, right? We don't know. So what can we do? Well, what we can do, I've got it written out here. I'll show you another way here. This thing is greater than or equal to, this is kind of clever, 1 over 2 times the square root of n for n greater than 25. Let's see. Let's let's think about this, okay? So let's start. That's what I have claimed. Let's start from scratch. So let's start with this thing here. The square root of n plus 5 I want to claim is smaller than 2 times the square root of n for n greater than or equal to 25. Is that right? As long as you're greater than 25, then you can write square root of n plus square root of n. And as long as you're greater than or equal to 25, this is going to be greater than or equal to 5, right? So as long as you're greater than or equal to 25, this is the case. And since this is the case, now I can go back and get this. This is the same as 2 times the square root of n. And now if I flip them over, 1 over that is smaller than this. I'm sorry, is greater than this. Okay, and now I can look at this one and I can say, what do I know about this? Heck, this is just a constant. That's a constant. I can bring that out front. And now I've got exactly something that I know. Here's the p-test. This thing diverges. It diverges to infinity. So since this thing diverges to infinity, 1/2 of it will also diverge to infinity. And what do I know? I know that since when I add up all these things, this thing diverges to infinity. And these are all bigger than these will as well. Okay, so there you go. Okay, how are we doing time-wise here? 36. I might as well show you one more thing. It kind of fits right in with what we're doing. Here's another way of doing this problem. Another way of doing it is just saying, basically, for big N, this 5 here really doesn't matter. It really doesn't matter. These things here are going to act very much like these things here. They basically act the same way. And actually, this is just enough different that I guess I'm gonna hold off to that. I'm gonna go to the next video before I show you this. There's not much to it. No, heck, let's just do it right now. So the point is, here's what we do. We say these things here and these things here pretty much act the same. And so the theorem says this. Here's the theorem. It says if the limit of a sub n's and b sub n's as n goes to infinity is equal to L, where L is these things are all positive number, some positive number, and I'll just be clear here, and all the a sub n's and b sub n's are let's say greater than 0, so we don't have to worry about things being 0 in the denominator. Then this, I'll just write up, then I'll just say it this way. Either they both converge or they both diverge. Okay, another way of saying it is this thing converges if and only if b sub n converges. Okay, one converges if and only if the other one converges. So they both do it the same way because they're both acting basically the same way. Okay, so this thing right here, if I just look at the limit of this thing right here, remember how to do the limit? I take the limit of this thing as n goes to infinity, and I can flip this one up on top, and I'm going to get the limit as n goes to infinity of the square root of n divided by the square root of n plus 5, and then you divide both the top and the bottom by the square root of n, and you're going to get 1 over 1 plus 5 over the square root of n, which the limit of this, which is equal to 1. So basically, we know that this thing converges. We know that this thing converges. And so since that thing converges, so will this one. Okay? Let me show you another one where this stuff is really helpful. Okay? It's a really nice theorem. Yeah, And it is pretty straightforward, okay? Let's look at this. 3n squared plus 5n minus 8 divided by n to the fourth minus 12n third, or make it squared, I don't care, squared plus 8n plus 7. Something like that. Okay? So here's what I do with that. Let me make sure that you're all on here yet. Here we go. Okay? So what do? I say, I first have to know the answer before I even begin. So I look at this and I say, what is this thing going to look like in the long run? In the long run, these things here don't pay much, never mind. The highest power up here and the highest power down here are what really influence things. And I notice that the highest power here is 2 greater than the highest power here. So I look at that and I say, this thing here really acts pretty much like 1 over n squared, because this is 2 greater than that. So that's my thinking, okay? That's my thinking. So here's what I do. I just take the limit of this whole thing here, 3n squared plus 5n minus 8, all over n to the fourth minus 12n squared plus 8n plus 7, and I compare those things with 1 over n squared. See that? I compare those with 1 over n squared. Now the rest of it is pretty mechanical. What do? I want to find this limit, so I flip this up to the top. When I flip it up to the top, it's going to be multiplying this by an n squared. And so now I'm just looking at that limit. Then how do I evaluate that limit? I divide both the top and the bottom by the highest power of n on the bottom, right? Highest power of n on the bottom is n to the fourth. And by the time I do that, okay, we've done enough of these. I'm going to let you kind of figure them out on your own here. But I can first multiply, well, I can multiply this by this first, then multiply it all the way through. I'm going to end up with 3 plus 5 over n minus 8 over n squared by the time I'm done. And on the bottom, I'm going to get 1 minus 12 over n squared plus 8 over n cubed plus 7 over n to the fourth. And now you can go boom, boom, boom again. Boom, goes to 0, 0, 0, 0, 0, 0. It goes to 3, which basically means that these things here act pretty much like these things there. And this thing here, I could just bring the 3 outside and it's going to converge. So basically, since this thing converges, yeah, I already had to erase the middle stuff here. But since this thing converges, then so will this, because the limit of these things divided by this gives us 3. Okay, and so 3 times bigger, not a big deal. Okay, let's try one more. Let's just try one more. Show you how it works. Okay, let's do this. How about this one? Square root of 5n squared plus 8n plus 7, all divided by n. Oh, let's see, what should we say? Let's make it, I tell you what, let's make this one cubed and make this one cubed. N cubed plus n squared plus 8. Okay? N squared plus n plus 8. Okay? Just make it like that. N cubed plus n plus 8. Okay? Can you tell me what that's going to do? Is that going to converge or diverge if I add all those things up? Well, here's the way I look at it. I kind of think it looks to me like the highest power of n on the top is n to the 3/2. And it looks to me like the highest power of n on the bottom is n cubed. And now I look and I say, what's the relationship between these two? This is equal to 1 over n to the 3/2 power. See that? This is equal to 1 over n to the 3/2 power. And what do I know about this series? What do I know about that series? This series here is going to converge from the p-test. Agreed? That converges by the p-test. So all I have to do here is I take this thing right here, n cubed plus n plus 8, and I divide that whole thing by 1 over n to the 3/2. And I take this limit as n goes to infinity. And if you do that, I think you, you're going to end up with, you do all the work there, and you're going to end up with the cube root of, with the square root of 5. The square root of 5 by the time you're done. And so what does that tell you? That tells you that since this thing converges, so does this. Because it's basically just the square root of 5 times bigger than these. Okay? So there you go. So those are all the various ways you can compare one sort of a series with another series. Okay? They all work that way. Okay, very good. In our next video, we're gonna I saw a book once that mentioned all these things were called extrinsic tests. Extrinsic. How do you spell that? Extrinsic tests, meaning that you compare them with something outside of themselves. You compare them with another integral, or you compare it with an integral or with another series. Okay, they're extrinsic. The next tests that we're going to look at are called intrinsic, or that'll be coming up pretty quick. Intrinsic, where you don't have to compare them with another series. You look at the series itself, and you kind of look and you say, how does this thing behave all by itself? And so there's a collection of intrinsic tests. So that's coming up. Okay, very good.